if a system is linear? Somebody said it, I heard it. Homogeneity, yes. So basically, we can apply a couple of tests, and it comes down to the fact that if the system output is the sum of the function inputs, it's linear. So we can say that, here I go trying to remember things off the top of my head again. So correct me if I'm wrong. A1 of x1 of t plus a2 of x2 of t is going to be equal to what is it? A1 y1 of t plus a1 y2 of t. Is that right?
Looks right.
Superposition, homogeneity. Time invariant. What's that mean?
If the process, like, it has the same output at different stages of time. Like,
Same output, meaning that you can shift the input and put it through the system, and the output will still be the same. What are the easy ways to see if a system is not time invariant?
at the on the outside or something like that.
What about time scaling? You remember that? So it is not time invariant if it has time scaling. And what is time scaling? Y of t is equal to x of at. That's time scale. That's not linear time invariant. I think there was another thing that made it non-time invariant. T squared. Yeah. If it has a y of t is equal to x of t squared. Thank you. You see these, they are not time invariant systems. Right?
Mm-hmm.
Is any of this coming back?
Yes.
Slowly? Fast? Quickly? Okay. All right. What about causal? Causality. What is causality? You don't look into the future. Exactly right. So the output of the system always works off of past values on the input. You do not look into the future. All right. Okay, we just covered our first 3 lectures. Okay, 2 lectures. The next lecture, impulse response and convolution. Is convolution going to be on the test?
Yes.
Okay. I don't. Does everybody feel comfortable with graphical convolution now? What are the steps?
Shift.
Flip. Shift. Multiply.
And accumulate.
And then accumulate. Accumulate, so let me write those down. Graphical convolution. All right, step number 1 is flip. Step number 2 is shift. Step number 3 is multiply. Then integrate, accumulate, find the area under the curve, whatever you want to say here. So I'm going to give some advice on these real quick. When you do graphical convolution, take your time. Do it once. Burn a lot of paper. It doesn't matter. You know, draw little graphs for every stage of the process. You know, the majority of the quizzes that I saw when we did graphical convolution, I could see there was one little tiny graph up in the corner. And you had drawn over it and over it and over it and over it and over it. So you could barely tell what it was. You know what I mean? It's okay if you use 4 or 5 sheets of paper for one problem. That goes for the quizzes too. If you run out of sheet of paper, grab a new sheet of paper. Right up the top right corner, 2 of, just keep adding pieces of paper until you get to the end. We're sadly not environmentalists right now. So don't worry about it. It is much more important to see clearly where you're at than to try to conserve paper. Yeah?
So is there like a pattern with convolution? So for example, like with multiplication, if you multiply like a scalar by a scalar, it's like another scalar, or like a line by a line, you get like a quadratic function. Is there any like kind of pattern to it to where you can kind of check yourself after?
There are a couple of things. So one of them is symmetry. If you have something that's symmetric going in on both sides, you should get something symmetric on the output. Right?
So it's symmetrical both x and h.
Yeah. Yep. Another thing that you kind of, after a while, you start to see it. You have to think about how they, I don't want to write that, how they form up together. So let's say that you have this. You have a rect function. You have some triangle. And this is the guy who has the t data point. You got to keep track of where t is at. Always know where t is at. Okay? And as you grab this t and you move them through, when these two start to overlap, it's going to create a curve on the output. Does that make sense? Because as you start to multiply these two together, at first it might just multiply like this little tiny corner down here. And then the next graph you draw, move t forward just a bit. Okay? And the next time, this next delta t, whatever you move it forward to, you know, it might add this little region of the triangle. Then you're going to move it forward another delta t, and that might add this region. Does that make sense? So each delta t increment that you slide this, it's going to start to add more and more and more. So that resulting output graph is going to curve up. Does that make sense? So think about things like that. It's more of getting a feel for it than rules like scalar in a line. Convolution is really something that you have to wrap your head around. And so you just got to do it.
And before you said we wouldn't have time to do the like the integral and stuff, we'd have to be able to do it by hand. Or just by looking at it, I guess.
I'm not going to make you do convolution by the integral on the midterm because I don't want you to spend that much time on it.
Okay.
So in order to get through the midterm,
Go quick.
you got to go quick. So what are the 3 things that I said are important in engineering? Long time ago, in the very first class, I said what? Organization, time management, the most important thing, problem solving. So you've got to be able to solve problems, and that's actually going to be the 3rd question. You have to be a problem solver. Organization, you get 1 page, one-sided, of handwritten notes. You need to be organized. Now the most important thing is time management. So when you're going through these, convolution, this should be the give me problem. You should be able to sit down and move this through and do it very neat and do it very organized and get through this problem quickly. Because this is geometry, you know, right? I'm multiplying a triangle by a square wave here. I don't know what I'm going to give. I haven't made the midterm yet. But does that make sense? So those are the 3 things that I try to test on too, because I think those are the 3 foundations of engineering. Okay. Multiply, and the result of the multiplication is what you find the area under that curve. By geometry, if you need to write out a quick integral just to see it in your head, that's fine. Just do it quick. And look for transition points. When this guy starts to touch this guy, that's a transition point. When this guy hits the beginning, that's a transition point, right? So there's a lot of transition points, and you can draw a lot of pictures to make sure that you don't miss any transition points. Got it? Yeah.
Yeah, and I forgot, how do you like know without integrals and stuff where the output starts? Like what value of t, I guess?
Okay, so when we look at this, let's assign some numbers to this. Let's say that this value is t plus 1, and this value is t minus 1. Okay? And this guy is going to be minus 2, and he's going to be plus 2. Okay? Now, think about it in your mind. I'm going to grab this t value, and I'm going to shift this whole triangle to the right. So this leading edge is moving. And the question is, when does this leading edge start to touch this? Because these are two different. This is h of t and this is x of t. And they're getting multiplied together. So if we're multiplying x of t by 0, it's 0, right? We're multiplying h of t by 0, it's 0. So you only start to get a result of this multiplication when they actually touch. So given this example,
So if you were to make a table, there's basically 6 permutations. Is that right?
yeah, in this
That you need
one,
to worry about.
okay, that's a good point. You can make a table. Yeah. All right, so when does it start to touch? At what value of t does it start to touch?
Minus 2.
Minus 1.
Minus 3.
Oh.
Always go, label these things, right? Always go by t. So let's draw this out. So here's this guy, and they're going to start to touch. And I totally messed up on scale on here. T plus 1, t minus 1, and this is minus 2. So if this point is minus 2, that's where they start to touch. That's actually t plus 1, right? So t plus 1 is equal to minus 2. Therefore, t is equal to minus 3. And if you have nice engineering paper, which helps on a test, you can also have those nice little boxes. And you can count boxes and put this up so it's at scale. So then you can just count how many boxes over it is. Does that make sense? Okay, so at t is equal to minus 3. So this is the shift. And this is going to be the multiply. And this is going to be the area. What do we get with this multiplication?
0 right there.
We still get 0, but it's starting to touch. So just infinitely, like a delta t later, we're actually going to start to get numbers. So for a multiplication, we still get 0. Area, we still get 0. So let's go just a little bit further. What value of t should we make now?
T plus 1 is greater than negative 2.
Yeah,
T minus
Minus
2.
t plus 1 is greater than minus 2. Yes, so t is greater than minus 3.
Yeah.
Pick a point. Specifically, 1 point. Pick a point.
Oh, negative 1.
Okay, negative 1. Let's actually go a little bit less than that. Let's go negative 2. So if we want to make t is equal to negative 2, and I'm going to try to draw this one actually to scale. So here's negative 2. That's where t is going to sit. This is t plus 1, t minus 1. I didn't want to go all the way to minus 1 because then it would be fully enclosed, right? And redrawing it this way, you now say, wow, I missed this whole ramp up. So if you want to, back up a little bit. Go to t is equal to negative 2.5 and draw another picture. Draw a lot of pictures. That's the easiest way to do this. So what do we get, though, at t is equal to minus 2? What does the multiplication look like of this guy?
1/2 2 times 1.
So if we were to draw it, that's the only thing that's remaining. And you were saying 1/2 t times 1, which
2
is
times 1, so like base times height.
base times height. 1/2 of that, because it's a triangle, right? Does everybody see how I got the multiplication?
Mhm.
Let me use a different color up here. So the blue is one equation. Okay, that doesn't help. Let's try this one. No, that's a little bit better. So the purple is one equation, the black is another equation. When they get multiplied together, you can go point-wise if you want to. What is the purple value here? Something greater than 0 and less than 1. What's the black value here? 0. Therefore it's 0. Do you see how we got this one? Now, let's put some values on here. What is this value? -2. What's this value?
-1.
What's this value? Now we can use geometry. So exactly what you said. This is terribly out of scale, but it is 1 times 1 times 1/2. So that gives us 1/2 for our area. All right, so we keep moving this thing in. So what's going to happen between the 0 and the 1/2? Exponential growth. Why is it exponential growth? Because as we move this in, first we're adding this little tiny area, then we're adding this bigger chunk, then we're adding this bigger chunk, and this bigger chunk. So we know as it moves in, it's going to start to accumulate area faster. Does that make sense?
Yeah.
All right, so let's continue our table. What's the next value we should do? And there's no wrong answer. You just pick a value, put down. -1. Great. So let's draw another picture at t is equal to -1. At -1, our triangle is going to sit here, and again, this is t. This is t plus 1, this is t minus 1, and this is -1, this is -2. All right, so now what does the multiplication look like of those two waveforms? Triangle. What's the area?
Area of the triangle.
1. Because now we have this one doubled. Right? Okay, so now we see that this guy is fully enclosed in this rect function. So let's pick another value. What's another t value that we can go to?
T equals 1.
Let's go one more in the middle there. How about t is equal to 0? Because you see where it's going already, right? Let's do one more intermediate step just to double check. Because maybe we're not 100% sure what the shape is going to be next. So what's this look like at t is equal to 1? Or t is equal to 0, I'm sorry. Right?
Yes.
What's the multiplication at t is equal to 0 look like?
1 again.
The area is 1. This is all organization, right? Draw a lot of pictures. And if you're not sure what the shape looks like, draw more pictures. And it'll give you the shape. All right, so we made it all the way to t equals 0. What do we know about these two shapes?
Symmetry.
Symmetric. What's that mean about the convolution output? All right, now, how do we take what we've done now and actually get the output? Now, if we have kept everything very nice and organized, and like I said, maybe we make a table. A table is a great way to keep things organized. All right, so now we plot, given the table, what are we plotting?
The area.
Area. Convolution acts on two functions, and it gives these area outputs. All right, so at t is equal to -3, what's the value? 0. T is equal to -2. What's the value? 1/2. I'm going to draw this dramatically out of scale. T is equal to -1. What's the value? 1.